I'll tell you how you can remember this program and all. Okay, and also I'll tell the logic also. Okay, the main program flow for the implementation of DIT FFT is shown in this figure here. In this flowchart, is they shown here. The subroutines used are underscore clear to clear all the memory location reserved for the results. Underscore bit reverse stores the data sequence x of n in bit reverse order, and underscore butterfly computes the four equations of computing real and imaginary parts of the butterfly structure. Here, this is the butterfly. Okay, this is the output. Using x of 0 and x of 4, this is first output. Okay, so is second output, third and fourth. Here the inputs are real and imaginary. The output also, the first output is also in real and imaginary. Here also real and imaginary. Okay, we stored the result as real and imaginary. Just remember, and the inputs are in bit reverse order in this way. And also here we can clear the locations reserved for the clear all the memory locations reserved for the results, and also bit reverse program, subroutine program. And butterfly computes four equations of computing real and imaginary parts of butterfly structure. Yeah, we already discussed about this. Okay, how we can calculate the AI dash, AI dash, BI dash, and BI dash. Here we consider the 2-point FFT computation. Okay, we derive the equations AR dash, AI dash, BR dash, BI dash. These are the outputs of the DFT. Okay, but it computes the four equations of computing real and imaginary parts of the butterfly structure, and also underscore spectrum computes the spectrum of x of n. Okay, here how many times we can invoke the butterfly program? Okay, each butterfly program subroutine means subprogram which consists of four equations. Later we will discuss about that. How many times we can invoke? We can call it, because here, see here, 1, 2, 3, 4. 4 butterfly in first stage, in second stage, 1 and red color, 2, 3 and 4. Again here second stage also 4. In the third stage also 1, 2, 3, 4. Again 4. That means how many butterfly? 4 plus 4 plus 4 means here 4 into 3, 12 butterflies. Okay, that's why we can call the butterfly subroutine 12 times. Butterfly subroutine 12 times, and other subroutines are invoked only once. Okay, just go through this main program flow. Okay, start, then invoke clear all the memory location reserved for the results, and invoke butterfly program. This program for keep the inputs in bit reverse order, and set appropriate operands for butterfly. Then invoke butterfly program and invoke spectrum program. Spectrum for inputs and n. Okay. First here we'll discuss about the clear program. Okay. Before that we can initialize some memory locations. See here .mmregs. Okay, this is the memory mapped registers. Okay, dot definition underscore c underscore int int 00. Wait a minute. Is it audible? Hello? Yeah, okay. Then here dot data initialize the inputs data, then reserve wait location for x of n. So that is data here. Okay, and x of n is in Q15 notation. X of n is in Q15 notation. Okay, then here first we will discuss about the clear subroutine. Discuss about the clear subroutine. See here, 16 location mean for final results are clear. AR2 is used as pointer to the locations. Okay, AR2 is used as a pointer to the location. See here, why 16 locations? Why 16 locations? Because here 8 outputs, each input will consist of real value and imaginary value. Like 8 outputs, okay, in 8 output, one real value in the imaginary value. That means here total 16. That's why here the AR2 is 16 locations can be initialized. Sorry, yeah, here AR2 is used to pointer to the locations. Okay, see here, first location x0 or x0 or AR2. Okay, here this AR2 points to the FFT data memory. Okay, store in AR2 as 0. Store AR2 0. See, repeat hash 15. That means the next instruction what it is, that instruction can be repeated 16 times. We already know that about the repeat instruction. Okay, here x sub k is equal to 0. Again, AR2 plus means AR2 incremented by 1, AR2 plus 1. Okay, then here RC equal to RC minus 1. If RC equal to 0, okay, if it is 0 means, okay, return. Okay, return to the main program. Otherwise, return to here only. Again, the next x sub k becomes 0, and means here up to 16 times the x sub k values, x sub 0, x sub 1, x sub 2, all becomes 0. Here we can initialize all the locations to 0. Clear. Whatever the value which can be stored in the x sub k, okay, that can be erase it. That means we can initialize to 0. Okay, just practice this program. Clear program. Particularly, he will ask, write the clear subroutine program for FFT computation. Okay, please go through this. This is very, very important. Okay, this instruction can be repeated how many times? 16 times. When this repeat instruction the RC equal to RC minus 1, when it becomes RC equal to 0, repeat counter equal to 0, then this return to the main program. Return to the main program. If it is not equal to 0, again will come here. Initialize 0 to all the instructions. Sorry, all the memory locations. Just go through this. This program is very important. Please practice it. Okay, either you can practice it, either you can remember. Okay, go through the logic, which logic they use. Okay, this is about the clear. Okay, next here we'll go through the bit reverse subroutine. Here, this one, bit reverse subroutine. Before that, here AR1 is used as pointer to x of n. AR1 is used as pointer to x of n. AR2 is used as pointer to x of k location. Just remember, AR auxiliary register 1 is used as pointer to x of n. AR2 is used as pointer to x of k location. Okay. AR0 is loaded with 8. AR0 is loaded with 8 inputs and used in bit reverse addressing. Bit reverse addressing. Here, instead of n divided by 2 equal to 4, n divided by 2 equal to 4, it is loaded with n equal to 8 because x sub k requires two locations, one for real part and other for imaginary part. That's why n equal to 8. Thus, x of n is stored in alternate locations which are meant for real part of x of k. AR3 is used to keep track of numbers of transfers. Okay, just AR1 is used as pointer to x of n. AR2 is used as pointer to x of k location. AR0 is loaded with 8. Okay, AR0 is loaded with 8 and used in bit reverse addressing. Just remember. AR2, AR1, x of n, AR2, x of k. Okay, see, go through the equation here. STM has x0, x0, comma AR1. That means here AR1 points to x of n0. Then STM has x0r. I mean first output. Right? Okay, here the AR2 points to XOR output. AR2 points to output, AR1 points to input. Okay, now you can store index, means the STM has 8 AR0. Okay, AR0 is loaded with 8 value and 7 AR3, means here we can repeat the same process 8 times. Okay, 0 to 7 he mentioned here. STM load 7 into store 7 into AR3. Means how many times? Count 7. See here. AR3 is used to keep track of number of transfers. Okay, just remember this. Now loop load AR1 into A. Load AR1 location. What is the address of the AR1 into the A value accumulator? Now STL store A comma star AR2 plus 0B. Okay, here copy x of n to location of x of k in a bit reverse order. In a bit reverse order. Okay, BANZ loop. BANZ loop. Jump not equal to 0. Jump not equal to your branch instruction. This one is branch instruction. Okay, here star AR3 minus. That means here after completing this instruction, there is a loop here. How many times it will repeat? Up to 7 times. Okay, star AR3 minus means AR3 is loaded with 7. 1 is equal to 0. AR3 equal to AR3 minus 1 becomes 6. Again it becomes 5, 4, 3, 2, 1. Okay, when it is equal to 0. Okay, no. If it is yes, AR3 equal to 0, yes, return to main program. If it is not equal to 0, again repeat the loop. Okay, just remember this one. Okay, here AR1 points to the x of n, AR2 points to the output, AR0 is loaded with 8, means 8 location, that's why. Okay, and AR3 is loaded with 7 to keep track of that one. Now the most important is butterfly subroutine. Most important is butterfly subroutine. Here, just remember, go through this. This is very, very important. I already told that butterfly subroutine is invoked how many times? 12 times. Butterfly subroutine is invoked how many times? 12 times. In each stage, 4 butterflies. In the 3 stages, total how many butterflies? 12 butterflies. That's why we can repeat the, okay, you can call the butterfly subroutine how many times? 12 times. Here the part of the subroutine is shown in figure 6.13 here. Okay, real part and imaginary part of A and B input data of butterfly structure is divided by 4. Why it's divided by 4? See here. Here, what is meant by the 1 divided by 4? What is meant by 1 divided by 4? that is scaling the inputs. That means to scale inputs, what we can do? We can multiply each input by 0.25. 0.25. Just remember, 1 divided by 4. We did that one only. Divided by 4, that means 1 divided by 4. 1 divided by 4 is scaling factor, 0.25. He mentioned here, scaling factor. Okay. Next here, real part of A data which is divided by 2 is stored in temporary location. Okay, it is stored in temporary location. It is used further in computation of equation 3 and equation 4 of butterfly. BR dash and BI dash equation. Okay, real part of A data which is divided by 2 is stored in temporary location. It is used further in computation of equation number 3 and equation number 4. Division is carried out by shifting the data to the right by 2 places. Okay, how we can carry the division? Okay, here we can divide the each inputs by 4. Okay, for that purpose, we can use the shift operation. If we shift right 2 times, it is equal to divided by 4. Okay, and the AR5 points to the AR5 points to the AR5, which points to the part of A input data, real part of the input. Just remember, AR5 is real part of the input data. AR2 points to real part of the input data. AR3 points to real part of the total factor. Just remember, AR5 real part, AR2 real part of the AR5 real part of the input data. AR2 real part of the B input data. A input and B input, and AR3 which points to the total factor. Just remember, total factor while invoking the butterfly subroutine. After all the 4 equations are computed, the pointers are in the same position as they were when the subroutine is invoked. Thus, the results are stored such that in place computation is achieved. Okay, here this is the subroutine program. Okay, here this program is for this one. This program is for scaling. This program is for scaling. Load AR5, comma -2, comma A. Store lower bits of the A in AR5 register. Here AR5 which points to the which value? Real part of the input data, right? That's why. Okay. Here AR5 -2 means it's shift 2 times right. Okay, that is this program is equal to replace AR with AR divided by 4. Real value of the input divided by 4. Just remember this. Okay, and store that AR divided by 2 in temp1. See here, temp1 means store #temp1 in AR4. That means here temp1 in the AR4 register. That's why store A comma 1 store A comma STL A comma 1 comma or AR4 plus. That means here store AR divided by 2 in temporary register. That means which register here is AR4. Next, similarly for imaginary values. Again, input can be imaginary value of the input also divided by. That's why load star AR5 comma -2 comma A. Okay. Again, then store A comma star AR5 minus star AR5 plus, in that real value is stored. Okay. Star AR5 minus their imaginary value is stored. Again, that is equal to AIM with AIM divided by 4. Imaginary value of the input is divided by 4. -2 means shift operation. Whatever the contents of AR5, it can be shifted 2 times and stored in the accumulator. Again, that accumulator value is stored in the AR5 minus. So star AR5 minus means imaginary, star AR5 plus real. Just remember this. This one is real, this one is imaginary. Plus stands for real value, okay, minus stands for imaginary. And similarly, you can go for the B input. See here, AR2 points to the real part of B. Okay, that's why load AR2 comma minus 2 comma A. Okay, that means AR2 means BR value. Okay, minus 2 means divided by 4. That's why after divided by 4, store the accumulator value, whatever it is. That means BR divided by 4 in AR2 plus. That means here which holds the real value of the B input. Then similarly, AR2 minus, same as it is. AR2 minus, that means which carries, which stores the imaginary value. Okay, load star AR2 comma minus 2 comma A. Okay, then store A in the AR2 minus. That means replace BIM by with BI divided by 4. Just remember this program. This one is scaling program. This one is scaling. Okay. Next here, consider the butterfly equations. How many equations? Total 4 equations, right? AR dash equal to this one. AR dash equal to AR plus BR into WR minus BI WI. This is one equation. Okay. This is second equation, third equation, and fourth equation. See here. Consider this equation. AR equal to AR plus BR into WR minus BI into WI. Okay. Initially, load the accumulator with 0 value. Load accumulator with 0 value. Then he did multiply. Just remember AR2 plus BR. Okay, AR2 minus BI. AR3 minus WR. AR3 plus WR. AR3 minus WI. Just remember this. Okay. First he perform this one, this part. Multiply AR2 plus AR3 plus. That means BRWR. Next, he subtracted this one BI into WI. Here, whatever the contents of this BRWR in accumulator, right? Okay, that's why MAS. Multiply, accumulate, and subtract. Here already we have A value here. In that A, what do we have? BRWR. This BRWR is, okay, is subtracted by AR2 minus. Okay, see first here multiply here. AR2 minus and star AR3 minus. What it is? What it is? Star AR3 minus and star AR2 minus this one BI into WI. Now multiply this, first multiply, then subtract this one by A value. What is the A value? BR into WR. That's why. Then again stored in the accumulator. A equal to BR into WR, this value minus, that means A value, this one. A into BI into WI. That means here this one. AR2 minus and AR3, one is minus. Okay, AR3 minus. Okay, this one. Now add. Now this part is completed. This is in accumulator, right? Again we stored in the accumulator. Accumulator will consist of this part. Then which is added to AR, right? AR means AR5 plus. So here add star AR5 comma 15 comma A. Here what it mean? AR5 means already it's 15 bits. Again here we can make it to 32 bits. 15 means we can make it to 32 bits. That's why this instruction. Just remember this. Then it becomes A equal to AR plus BR into WR minus BI into WI. Add hash 1 comma 14 comma A. Round and store in the AR5 plus register. AR5 plus, which holds the AR dash value, real value of the first output, butterfly output. Just remember, this one is AR dash. This program is for AR dash. Now we can consider the AI dash. I'll change the color here. AI, this one is AI dash. Already we know that equation AI dash equals AI plus BI into WR plus BR into WI. Here for imaginary value of AR5 minus BR, AR2 plus AR3 minus here, okay, here AR3 plus, here BI means BI means AR3, AR2 minus AR2 minus. Okay, again load 0 into A register. First he perform the BR into WI, this part. He perform BR into WI. Here load hash 0 into A, then MPY multiply AR2 plus. AR2 plus means this one BR. AR3 minus means WI. This one is AR3 minus, this one is plus. This one is AR3 plus, this one is AR3 minus. See here. Next, again MAC unit. Multiply, accumulate, and store in the register. Already A, which consists of BI into WR. Sorry, BR into WI. Then you can multiply this part and add it with this one. Okay, that's why MAC, already we have A value. Multiply and add. First multiply AR2 minus, that means BI. AR3 plus, you can write here. AR3 plus. Otherwise you can write AR3. Star AR2 comma minus star AR3 plus, multiply this one. This means this one BIWR. Then added with A value. What is the A value? This one. Added this one. Again accumulated in stored in the A register. That means A, which holds this part. Okay. Next, what we can do here? Which one is left here? Now this part is left. Which one? This part. This one is already we did. We can do the addition. Okay, same. Add AR5 plus, sorry, star AR5 comma 15 comma A. Here we can make 32 bits. We can make load the for output. We can make 32 bits to avoid the overflow. That's why A is equal to AI plus BI into WR plus BR into WI. Now just practice this for instruction. Add hash 1 comma 14 comma A. Store higher bit value A comma 1. See, star AR5 means which holds the AI dash value. Which holds the AI dash value. Okay. Just remember this. Now BR dash equation and BI dash equation. Here BR equal to AR minus BR into WR minus BI into WI. Okay. Then here, what is AR4 plus comma A? Load AR4 plus comma A. We perform load A with AR scaled by 2. Wait a minute here. Okay. Here load AR4 plus comma A. What is this? Here load A with AR scaled by 2. Already we did scaling here. Okay. Here we did the scaling. Here whatever the value which can be stored in the AR4 after scaling. See here AR4 plus and AR4. See here where you can use it AR4